Projectiles problem. A stone is projected, 35 is the initial speed from point 0, horizontal ground, projected at an angle of alpha. We're given alpha, and we're told that at time t, the horizontal distance from 0 is x, and time t, the vertical distance is y. Using the model, prove this to be true. Okay, let's have a go at that. I'm going to add the horizontal and vertical speeds onto the diagram, and we'll work on from there. So as you can see, the 6 marks on offer here is a high proportion of the question, so we're going to have to consider both the horizontal and vertical motions. And notice also this equation does not contain t. Horizontal and vertical motion equations will contain t, but we will be able to remove that by using simultaneous equations. So let's first of all consider the horizontal motion. Horizontal motion will be constant. Speed is equal to distance over time because there is no acceleration. So I can say that the speed, which is 35 cos alpha, is equal to the distance, which is x, divided by the time. So t is equal to x over cos alpha. Now let's get a value to cos alpha. We're given that tan alpha is 3 over 4. Here's the triangle that fits, so therefore I can say that t is equal to x over 35 multiplied by 4 over 5. The 5 goes into the 35 7 times. So I get that t is x over 28. Now vertically, and this is going to be suvat, s is y, u is 35 sine alpha, v we're not interested in, the acceleration is negative 9.8, because I'm working suvat in a positive direction, and the t is t. The equation that links everything is s equal to ut plus a half at squared. And if I work that out, I get that y is equal to 21t minus 4.9 t squared. And if I substitute my value for t, I get that y is equal to 21x over 28 minus 4.9 over 28 squared, x squared, which does indeed cancel down to their requirement, so this is equal to 3 over 4 x minus 1 over 160 x squared. And there's the proof and the answer for part A. Part B, we've been asked to use the answer to part A or otherwise find the length of OA. Well, the length of OA will be a value of x, but the significant thing about OA is that y is equal to 0. So if I substitute y is equal to 0, I should get an answer for x. I can first of all multiply through by 4. That'll get rid of this, so I get that 0 is equal to 3x minus 4 over 160 is 1 over 40 x squared. I can now multiply through by 40, and I get 0 is equal to 120x minus x squared. So one solution to this will be x is equal to 0. Well, we know that that's a perfectly good solution, but it's not the one we want. And the other solution is that 0 is equal to 120 minus x. So therefore, x is equal to 120. And that's the answer to part B. Now in part C, we've been asked to find the greatest height that the projectile achieves. And they're suggesting we use the model. Well, the normal way, of course, is to just consider the vertical motion, and at this point where the particle is at the height of its travels will be when the speed instantaneously drops to 0 as it turns direction and heads back towards the ground. But using the model, we can do the same thing. And it's because we found the total distance from O to A. The greatest height will be achieved at halfway along that value. So this is the point where x is equal to 60. So if I sub x is equal to 60 into our model equation, I shall get a value for y. And if I work that out, I get a height of 22.5 metres. And that's the answer for part C. So I've done a bit of rearrangement to allow me to have some space to answer question D. The model now is refined to include air resistance. Using the new model, the greatest height of the stone above the ground is found to be K metres. State which is greater, H or K, justifying your answer. Well, if there is air resistance, the particle is being slowed down the whole of its journey. It won't reach A, for example, and it won't get as high as it did. So it won't get up to the value that we found for the maximum height in part C. So I'm going to say that K will be less than H. This, of course, is the value of H. K will be less than H with air resistance. And for part E, we're asked to state one limitation of this refined model. Well, I suppose the biggest limitation of the model is that we're still considering this particle, now subject to air resistance, as a particle. And that's not going to happen in real life. So that would be one limitation. The other limitation is the value of G that we've put onto everything. This is not constant over the whole of the planet, and we would need a better measure for G. So either of those two quoted limitations will earn you the 1 mark. And those are the answers for part E.